Okay, so let us start. Welcome to the second day program of so-called scientist stage of Vigyan Samagam. I now request Professor Ajit Parmeshwaran from ICTS TIFR Bangalore to chair the session on LIGO and conduct the rest of the proceedings.
Thank you. Very good morning, and let's get started with the LIGO India session. We will have two speakers in the session, Professor Patrick Brady from the University of Wisconsin at Milwaukee, and the spokesperson of the LIGO scientific collaboration. And he would give the keynote address, and followed by Professor Tarun Sauradeep of the AYUCA, as well as the LIGO India project. And this will be followed by a panel discussion involving Professor Bala Iyer of the ICTS, as well as the Indigo Consortium, and Professor Rajesh Gopakumar of the ICTS, and Dr. Dilip Krishnaswamy from the Reliance Geocom. So let me start with introducing the keynote speaker. Professor Patrick Brady is a professor of physics at the University of Wisconsin at Milwaukee. And as I said, he's the spokesperson of the LIGO scientific collaboration. His research interests are in different aspects of the gravity, both theoretical as well as the experimental aspects. In particular, the search for gravitational waves from compact binary systems as well as their multi-messenger counterparts. His work has been widely recognized. He has won several awards, and one of the most important ones recently is the Special Breakthrough Prize as well as the Gruber Cosmology Prize, which he shared with the LIGO Scientific Collaboration and the Virgo Scientific Collaboration. So without any further delay, let me ask Patrick to give the keynote address.
Let's see if this is working. Can you hear me okay? Great. So thank you very much for the invitation to come and talk at the start of this second part of Vigyan Samagam. Today I'm going to tell you a little bit about the LIGO project, Laser Interferometer Gravitational Wave Observatory, and I'm going to focus on what we've learned so far. But to get started, just to give people a chance to orient themselves about what gravitational waves are, I want to go back to Einstein's discovery of general relativity in 1915. With that discovery, he told us that when we think about gravity, thinking of it as a force isn't quite right. What we experience as gravity is actually the curvature of space-time. Now, often when I talk about curvature of space-time, students come up to me and say, but how do I see the curvature? What's the curvature? How do I know about it? And I basically tell them, look, you're sitting, and when you're sitting on that seat right there, you feel as if you're being pulled down, and that is you measuring the curvature of space-time. Now, Einstein, very soon after he introduced his new theory, he went to work on trying to understand some of its properties. And there'd been hints before that there should be these things called gravitational waves. And gravitational waves, in Einstein's theory, turn out to be generated when you take some matter. I like to think of my hand. You squeeze it down, you make it lumpy, and then you shake it around. And when you do that, you generate some gravitational waves which go streaming out into the universe at the same speed as the speed of light. Now, the second thing about that is that you start to wonder, with this prediction of the existence of gravitational waves from Einstein, what type of thing in the universe, in nature, generates gravitational waves? And this animation that was playing in the background gives you a hint about this. When we look out into the universe, we often see pairs of stars that go around each other. So I'm going to step back here for a second. The pairs of stars go around each other like this. And so you have two objects that are essentially dense and are shaking themselves around. And so they generate gravitational waves, and those gravitational waves propagate outwards from that binary system. Now, what we're going to talk about today are some special binary systems, those that involve pairs of black holes, pairs of neutron stars, and we'll talk a little tiny bit about a binary system that might contain both a black hole and a neutron star. Those are the targets that we go after with LIGO. Now, for those who don't actually think about gravitational waves every day, I want to remind you a little bit about what the effects are. How do we measure them? What's our antenna that we use to measure a gravitational wave? So to do that, what I want to start with is this image of empty space. I'm going to place a red sort of little ball in the middle, and then I'm going to, around a circle, sprinkle a number of yellow balls. And they're floating there, perfectly stable, in a circle that has a radius which is given by this letter small l. Now, when a gravitational wave passes by, coming from the back of the room, flowing through at the speed of light and passing through the screen, it has an effect on those particles that are floating in empty space. What it does is it stretches and squeezes them in a way such that you get a pattern like this. And this is the basic principle of what happens to material or to space-time also as a gravitational wave passes by. And it's kind of interesting to think back on the history of gravitational waves, because while Einstein predicted their existence and the recipe by which you generate them back in 1916, he had a slight error in his calculation, which he fixed later. But the understanding of gravitational waves took a long time. It wasn't until 1957 when there was a workshop in Chapel Hill in the United States where a bunch of gravitational physicists of the day came together and began to talk through what they understood about gravitational waves. And Felix Pirani had actually figured out how to think about how gravitational waves affect particles. And he presented that at the meeting, and he also at the same time presented the first sort of thought experiment that allowed you to conclude that gravitational waves carry energy. And the thought experiment basically took this sphere, or this circle of objects, and it put tiny weak springs connecting some of them. And so since you got the vibration of the particles, you had to actually deposit energy into the system. So in 1957, this was the first time that people really thought gravitational waves might have an impact on nature, although at the same time, the conference summary from that time actually has a lovely statement which basically says, you know, it'll be very interesting to work out what the effects of gravitational waves are on binary systems. Of course, astronomers know that this will be completely irrelevant for any studies of such systems in the future. That's kind of funny compared to where we are now, where we're now doing astronomy with gravitational waves. But still, I want to give you a sense of how you're going to measure them. So the next thing I want to note here is that if we take a look at the time when you've got the maximum stretching of these particles, and you talk about the distance delta L, which is the distance from the original radius to the maximum radius, or maximum distortion, and then you calculate a quantity known as the strain, or the distortion as I've already used. So it's the ratio of delta L divided by the original length. And here's where I want to give you a sense of how big that distortion is for things like black holes that are orbiting around each other and crashing into each other in the universe. The ratio is about 10 to the minus 21. Okay? It's pretty small. And to give you a sense of how small, this is about equivalent of a comparison of the width of a human hair to the distance to the next nearest star to us, which is 4 light years away. It would take light 4 years to travel to it. So this is an incredibly tiny distortion that you're trying to measure here on Earth, caused by objects that orbit around each other out in the universe. Now, there were a couple of false starts on ways to detect gravitational waves. Joe Weber is one of the best known who actually tried to use what we call resonant bars, so just big chunks of metal, essentially, which when a gravitational wave would pass by, they'd vibrate or ring like a bell. But around that same time, there was a great deal of interest in gravitational waves and gravitational wave detection. And in particular, then, there was this new thing. It hadn't been around too long. It was called a laser. And people had begun to understand that, of course, using a laser, you can now actually get these accurate measurements of distances. And since distortion means comparing distances, the question was, could you use lasers to actually build an instrument to measure gravitational waves? So Ray Weiss in 1972 set about a study which basically went through and thought about how you would build such a detector here on Earth. What were all the noise effects that were there? What would go wrong? What would go right? How you would make this thing work? And he wrote up a technical report which served in some sense as the blueprint for what became LIGO in the end. And the basic principle is here as follows. Many of you will have seen this video before. It's been used in certain high-profile press conferences. We're going to watch the laser go onto a beam splitter, go down 2 perpendicular directions, get reflected off mirrors at the end, come back to the beam splitter, and then part of the light will be recombined and put off onto a photodiode on the right-hand side. So let's watch this through. Now, as this happens, the 2 arms are initially of equal length, but if a gravitational wave passes, the 2 arms have distortions where one gets longer and one gets shorter. And so when the laser light is brought back to the beam splitter, it interferes in a different way depending on how much distortion is present. In particular, if you set it up with no vibration such that there's no light going on to the photodiode initially, but then a gravitational wave passes, you get this interference pattern, which leads to when there is a distortion due to a gravitational wave, there is laser light passed on to the photodiode on the right-hand side. So this is the basic principle that was brought about to try and build a gravitational wave detector, thought about by Ray Weiss in 1972. And the interesting aspect of this is that it took quite some time to try and realize it. One of the next steps that Ray Weiss himself did was he had a conversation with Kip Thorne while they were at a meeting in DC, and they spent a huge amount of time trying to talk through where Ray was explaining to Kip how the detector would work, and Kip was explaining to Ray what sorts of sources might be out there and what we might do, trying to figure out the scale for a detector that you might build. And it was then they began to realize that with the technologies of the day, you really had to go to not a desktop experiment, which is where Ray had started, but you had to go to a mega science project. You had to build something where that interferometer that's in that cartoon was 4 kilometers long from the beam splitter to the end mirrors. And so you had these L-shaped devices that would be 4 kilometers in length. They would have huge vacuum systems in them. They would have some of the best lasers you could build in the system. The mirrors that were used had to be specially coated. You had to take advantage of some really, really nice tricks that allowed you to cut back on all sorts of noise effects that would occur in the instrument. So it took them some time to get some money. They convinced the NSF basically in 1989 to fund it, and in 1992 money started flowing. And ultimately, at the end of the 1990s, the first of the laser interferometer gravitational wave observatories was built. This is an image of it. You can see a set of buildings down the bottom right. That's the corner station. The L shape that you see, which is characteristic of the current generation of gravitational wave detectors, it houses underneath a concrete structure a vacuum system that stretches for 4 kilometers from the center station to each of the end corners. And the lasers then are held in the center station and played around. Just again, to set the scale, I always like to do this for that's where the car is parked in this. So this is not a tabletop experiment. The second detector that was built for LIGO was built down in the southeastern part of the United States. The first one that I mentioned there and showed a picture of was in the Northwest. The 2 detectors were considered essential because we'd never measured these tiny distortions from gravitational waves before. But when you would use a single detector, it was always possible that vibrations of the Earth might be confused for a real gravitational wave signal. So the two detectors were extremely important. Now, in mega science projects, there's always some challenges. I've heard of, I was just listening just yesterday to some of the challenges that TMT continues to have. Here's a few of the challenges that we've seen when we were building the LIGO detectors in the US. There were the fires on the desert in the top left, came extremely close to the detectors. There were the canals that filled in down in Louisiana where some alligators took up home for a while. There was the emergency situation where, since in Hanford it's built on a nuclear, one of the nuclear test sites, they every so often do these various practices of some emergency happening, and the police car didn't realize that someone had put a 4-kilometer beam tube in the way, and so it was driving across the desert and ran into the side of the beam tube. Lots of stuff can go wrong. Stuff goes right too, though, and inside of the corner station, this is a picture of what is the situation with the current detectors as they're installed. Again, to just give you a sense of the scale that we're looking at, if I zoom in, that's a person standing there in the middle of what we call the LVA. So in the end, after a history that starts in 1916, gets its sort of first kickoff for these detectors in 1972, installs and finishes construction around 2001, operates the detectors for a while in through that decade. And in 2010, it basically, we've secured funding for an upgrade to the detectors inside, and so we rip out the first generation detectors and begin installation of the second. At this point, I want to go back and I want to just remind you where we are and what's a little unique. It's not totally, but it's somewhat different for gravitational wave detectors. Here on Earth, we want to have a network of them. There's multiple reasons. There's the fact that 2 detectors are needed to distinguish between a gravitational wave and perhaps disturbances here on the Earth. But there's also the fact that as we add more detectors, we can triangulate the direction to the source better. So having 3 detectors allows us to get good triangulation. But also, by adding more detectors, we can measure different polarizations of the gravitational waves that are generated. And this turns out to be a very key fact for the science that we can do. Now, I've given you sort of this history that has brought us up to 2010, heading towards 2015. In the meantime, the collaboration was established, and I wanted to say a few words about it because I wanted to make a connection back to India and the contributions that have been made so far by India in gravitational wave observations. So the LIGO Scientific Collaboration was formed in 1997. It was at that point a small group of people that hung out in a room about half or a quarter this size. By 2015, that group had actually grown to around 1,300 members. There are 860 authors within that group. There are 123 LSC groups, that is, individual institutions that join on to be part of the LSC. And they come from about 20 countries. The map of the world here shows you where they are, and if you look carefully, you'll notice it's somewhat small and hidden here, but there are a number of different institutions in India that are key players in the LIGO Scientific Collaboration. I actually wanted to highlight a couple of things. I mean, I think it's interesting to look back at how we got to where we are, and one of the things that we're going to notice in a little while is that a number of Indian scientists, for example, Bala Iyer, in the front row here, contributed to the early understanding of how black holes, binary black holes, evolve and how we might actually parameterize those and be able to measure properties of the systems. We also have people from IUCAA who started out and worked on the methods by which we might extract the signals from the data. And since then, of course, the number of participants in India has grown substantially, and there have been a large number of essential contributions made to the science of LIGO. So that brings me to the science. I've given you a bit of the history. I've told you about what the instruments look like, told you a little bit about how they work. And now we're at September 14th, 2015. And I remember that morning pretty well, going into the office. We were supposed to be just starting, not then, but a few days later, our first observing run with the updated instruments. And I got to the office, and I noticed my email is sort of going mad, which normally does, but it was a bit madder than usual. And I looked at it, and it's like, wow, we got something. And so that morning, during what was supposed to be an engineering phase, where we were beginning to tighten all the bolts and just get the instrument ready to go, we had our analysis codes running, and a gravitational wave signal had been identified. So that gravitational wave signal, I can never resist playing it back. Because the LIGO detectors are sensitive in the frequency band that is very close to our standard hearing band, you can play back the signal that we record in those detectors in a way that we can listen to it. So here you're going to see the signal played in two ways. You're going to hear it, and you're also going to see what we call a time frequency graph. The upper plot shows the time frequency evolution for Hanford. The lower plot shows the time frequency evolution for Livingston. And if you watch them, you'll be able to get your ear and your eye sort of sync up as you see something flash across the screen. So in full-on public talks, I always just comment that that's the most beautiful sound in the universe. It truly is. Every time I hear it, it's the same thing. It's just this magical thing. But that morning, we were beginning to try and tease out this information out of the gravitational wave signal with our first indications through a massive analysis run on huge computers, trying to assess the difference between signal and noise. And it took us quite some time to basically go through the process of validating at every level what the signal was, whether or not there was any way that we could have been mistaken by the way that the instruments operated, and somehow this was not a gravitational wave. And after several months of working hard on every angle, we internally concluded that this was indeed a gravitational wave detected at both of the LIGO interferometer sites that looked very, very similar, therefore, and came from a pair of black holes that collided out in the universe about 1 billion years before. So this trace shows a graph of the signal that we played back a few moments ago. The two colors are the same. One represents the data coming from the Hanford instrument. That's the kind of orangey color. The blue color So what was the signal that we measured? What did it come from? So another thing that I like to bring out at this point is, how do we know what these things are? And an analogy that I like to give for, again, just mostly for the public, is an analogy to when you walk through the park. And as you walk through the park, you hear different birds. And when you first do it, of course, you're a kid and you have no idea. You're chirps coming from all sides, and you don't know what bird is what or anything like that. But then you find a friend who's a bird watcher and understands what the different sounds are, and each time they tell you, oh, that sound, that's the sound of the warbler, that's the sound of the woodpecker, that's the, whatever it is. You build up a list of the different sounds inside of your brain. And so the next time that you're walking through the park by yourself, you hear a sound, and you essentially compare that sound to the list inside your brain, and therefore you identify, oh, right, there's a warbler over there. Okay. So in gravitational wave astronomy, we actually do a very similar thing. We go through, and we, for the sources that are these binary systems, we pre-compute the signal that we would expect. And we go through and calculate millions of examples of these signals, and we put them essentially into giant memory banks. We call them template banks. And then we compare those template banks to the data continuously as it comes in. And that allows us then to sort of identify, oh, that signal in that data is like this one over here. This signal on the data is like this one over here. And so by doing so, we're able to say what the source of the gravitational wave was. In particular, the type of work that began quite a long time ago, in the 60s in fact, to try to understand the impact of gravitational waves on binary systems, was started by Peters and Matthews. And they did a calculation that showed that if you took account of the loss of gravitational wave energy from a binary system, the two objects in the binary would slowly come closer and closer together. As they did, they'd sink deeper into their gravitational wave potential, and they'd have to go around each other faster and faster and faster. And eventually, they'd collide. Now, between the 60s and 2015, a great deal of work was done, theoretical calculations by the likes of Bala, a lot of numerical simulations by huge teams around the world. And this here is a simulation coming from one of the binaries that we detected in that first observing run. And you're going to see the evolution of the two black holes as they go around each other. Gravitational waves are being emitted, and as they're emitted, the objects come closer together. And you also see the trace of the signal along the bottom that we observe in the gravitational wave detector. So here's this in motion. You get the two objects going around each other. Gravitational waves are being emitted. The objects are slowly getting closer together, and as they get closer together, they orbit around each other faster and faster and faster, until eventually they touch, they collide. And when they collide, they quickly become a single unified black hole. The gravitational wave signal shuts off, and they just ring. They do what we call ringing down very rapidly. So this is the type of signal that we detected in LIGO on September 2015. The only thing is we only detected the very, 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 very last couple of orbits. Okay. Nevertheless, we were able to write up a paper, and I couldn't resist just including this photograph and this moment into the talk, because this was the press conference in Washington, D.C., a group of different representatives of LIGO at the time on the stage, just getting a photograph taken after the press conference. We'd announced gravitational waves to the world. We were all pretty excited. At one moment, though, I was standing around a room, and I can't remember if it was Bala or Tarun that was in the room, but there was a little bit of excitement going on in the room, and it's kind of what's going on? What's going on? And they were like, well, we're trying to figure out. Apparently, there's a tweet we need to see. And so the Prime Minister of India had tweeted that, LIGO India, we're going to do that too. So that moment was something that stood out for me that day, in addition to other things. And so it was a watershed day for LIGO India. Now, since then, we've continued to operate the two detectors in the United States. We've also linked together with our partners in Italy, so the Virgo collaboration in Italy, which operates a detector as well. We've carried out a second observing run, which was completed back in August of 2017. And at the end of that observing run, we had detected 10 collisions of binary black holes. And this animation shows you these binary black holes and their signals. The sounds in this case are not actually the sounds of the gravitational waves. They're just there to try and relax you and keep you calm. But it's a lovely animation. Each of these is a numerical simulation of the binary black hole collision that we detected played through for a number of seconds before they collide. Let me mention a few things to just notice about this. Things that you'll notice as you watch, you'll notice that the objects seem to have different sizes. That's because the size of each object reflects the mass of each object. You'll also notice that the length of the signal is different. That's because the amount of time that the gravitational wave spends in the band of the Earth-based detectors is different depending on the masses. So as we receive these signals, we build up a set of information about the masses of the different black holes that exist in the universe. And in particular, in fact, for the first detection, those masses were unusually big. So even with the first detection, compared to what we'd anticipated, we already had a superb new discovery about black holes in the universe. Now, I'm not going to let these all play through. You can get the Black Hole Orrery on the web. I encourage you to download it and take a look. I want to move on to the next big moment in our voyage so far, and that was August 17th of 2017. The signal from the gravitational wave detector, which was in the lower panel, and then also up above is the signal that was recorded in the swift gamma ray burst detectors. And when we play this along, you'll notice, first of all, the sound from the gravitational waves takes longer. It's got that beautiful chirping sound. There's a little ding. Actually, I have to play that again. Sorry, I just can't resist. I'll try to be silent for the ding. Okay, so the ding is there just to draw your attention. It, of course, wasn't a ding, but it's there to draw your attention to that peak that shows up in the graph at the top, which was the detection of a flash of gamma ray light by the Swift satellite. It came 1.7 seconds after the end of the gravitational wave signal. And this gravitational wave signal, just using it by itself, allowed us to estimate what were the two masses that were involved in this collision of two objects. And the masses were found to be down around 1.3 to 1.4 solar masses each. That's 1.3 or 1.4 times the mass of the Sun. That category of objects that emits gravitational waves like this and has those masses are known as neutron stars. They're essentially the end product of dying stars. They end up in binaries, and when they collide at the end of this merger process, they collide violently. They heat up immensely, and they emit these flashes of gamma rays. Before this event, it was hypothesized that neutron star binaries generated gamma ray bursts. But literally that day, I was in Amsterdam sitting at a sidewalk cafe trying to figure out what was going on. And that day, we knew something new. It was this amazing thing that we'd actually figured out, this association. Now, the interesting thing about this event was that it was the source that we thought would be the first one we'd see in many ways. It was the one we understood the best, or at least we thought we understood the best. And as a result, we had a bunch of partners, astronomers around the world, who were interested in looking in the direction from which we thought gravitational wave signals like this came. And the goal they had was to try and find a flash of light in other electromagnetic wave bands. So As we announced to our partners that we had seen this event and told them roughly where it was in the sky, which very roughly, hundreds of square degrees, we then set in motion a set of observations made by telescopes all around the world. This animation, I really like it. It was made by the Growth Collaboration, and in particular Varun Bolero, who's an astronomer here in India, was the one who was one of the people who was responsible for it. And what you see as this goes is you see the map of the world with daylight and night showing, and you'll notice as time passes that for every second that goes by, about 0.2 of a day goes by. And you'll gradually see, from the moment the gravitational wave was observed, you'll see certain points light up, and they indicate observations being made by telescopes around the world. So we start, and the early part of this, there's nothing, but then bam, the first night in Chile, the telescope in particular, the SWOPE telescope in Chile, actually made an observation of the sky in the direction, and it was able to find an explosion. So what it found was this image. This is the discovery image taken by the 1 meter 2 hemisphere collaboration using the SWOPE telescope. You can see a galaxy in the middle. That galaxy is NGC 4993. That galaxy is about 120 million light years from Earth. And the arrow points to a little blurry brightness that sits up there in the top left of the image. That night, the discovery was made by taking this image and comparing it to images that had been taken of that same galaxy by different telescopes and doing what astronomers call blinking it. So they basically wanted to blink to see whether or not the source was present. I'm going to show you an example, except the second image in this case is from 4 days later. And there's a kind of an amazing thing about this. So this was late that night. We'd already had about 12 hours or so of time between the event and when this happened. But right away, with this observation, the distance 120 million light years, and the exact time when the collision happened, we were able to compare the speed of light and the speed of gravitational waves with each other. And we were able to show that the two of those matched, should be at the bottom here. The two of those matched each other almost perfectly. The day before, we knew they were close. The speed of gravitational waves and the speed of light are the same. Okay? Absolutely phenomenal. Another discovery made overnight. Just beautiful. Now, the third thing that came out, and there's plenty more that came from this event, I'm going to mention a few more of them. The next one that came out was that before this event was discovered, there was some uncertainty in where the heaviest elements in the universe came from. Where did gold come from? Gold's pretty common here on Earth, and well, okay, it's rare, but it's still, there's quite a bit of it. And it was confusing where it came from. The studies and the follow-up studies of that optical flash and the associated what's called kilonova explosion were able to teach us that the heaviest elements are generated in the post-merger explosion that happens in that kilonova. And in particular, if you kind of go through and you want to sort of play with some numbers, roughly speaking, that collision generated about a Jupiter-sized mass of gold. Okay? So it's kind of nice to think about that. We should go out and mine it one of these days. Anyway, the one other result that came out of this observation, which was, again, just a beautiful result, and again, we knew it that night when we saw that distance to that galaxy. Gravitational waves allow you to measure the actual distance to where the collision happened. The observation of the galaxy gives us a thing which is called the redshift. It's how fast the galaxy is moving backwards from us. And Hubble famously gave us a relationship between that recession and the distance, which is related by a single constant called the Hubble constant. And so using this observation, we were able to make a totally independent measure of the Hubble expansion of the universe. And the result we got, not nearly as accurate as most modern results, but very, very nice. Comes in around 70 at the peak, 70 kilometers per second per megaparsec, sits right in the middle between two sort of measurements that are at odds with each other, perfect for us, and so on. So I'm going to wrap it up now. I've been told I have 2 minutes. I'll try and get it done with this. I want to tell you where we are today and where we're going next. We started observing Run 3 on the 1st of April. With observing Run 3, we now are into the era of routine astronomical observations with gravitational wave detectors. So far, we've told the world already about 22 low-latency gravitational wave candidates. We made public announcements of them within 6 minutes of the gravitational waves passing the Earth. We have seen that we're at a rate now with the sensitivity of the detectors in O3 of having about 1 every 5 days of binary black hole mergers, and we have 1 confident binary neutron star merger in the current set. But there was no electromagnetic, there was no light flash found associated with that event. We're going to run for another about maybe a bit longer, and so we're going to build up this huge list of different binary black holes, and we're going to learn so much about where they come from and how they are and what their masses are and so on. It's a really, really exciting run. But now I want to look forward again and show you again this map of the world that shows the different detectors. You look at it and you see the 2 LIGO detectors in North America. You see GEO 600 and Virgo in Europe. You see LIGO India, planned detector down here in India. And you also see Kagras, which is a detector that's under construction. Over the next decade, what we really want to do is to take each of these detectors, bring them up to very similar sensitivity, and operate them as a single unified worldwide network. The basic reason is that as we add each of these extra channels, we get to do more science. We get to tell you more about the nature of the object that generates the gravitational waves that we see. The plan over the next decade, and I only want to give you a rough sense of this, you should ignore the dates that are in the subject line here because things change all the time. But roughly speaking, middle of the next decade, we hope that we will have a further upgrade to the detectors in North America. We will have the detector in India, which will be built at the same sensitivity level as those A+ detectors in North America. And we'll have all of those operating in unison to take gravitational waves. The sensitivity should be about a factor of 2 further out into the universe to be able to see them. It's not quite, but it's close. And that means we'll see 8 times more signals than we can with the current generation of detectors. And so we'll be seeing signals down at several per day when it gets to that time, which is a real change from where we were on the 14th of September 2015. So with that, I'll finish. Thank you.
So while Tarun sets up his talk, maybe you can take a very quick question.
So you have pre-computed or simulated the waves or nature of the waves from different collisions, different objects. So I would wonder that how many different type of objects could be there in the outer space, and how big is your template table?
How big is the template table? Yeah, so we've got millions of templates. The number of templates, though, depends on how subtle the differences are we are willing to try and chase down. And so it can actually be way bigger than that. It can be tens and even hundreds of millions of templates. The calculations, when I say pre-compute, I'm exaggerating a little bit. It's sort of pre-compute in the computer science sense. The problem is solved in the sense that we know exactly what the algorithm is, but we haven't actually written down each waveform. So what we do is we compute them on the fly and make the comparisons. We're pretty well able to handle about 8 to 10 million waveforms in real time. We could probably go further than that. But right now, that's where we limit ourselves. The range that we look is we go down to about objects where each of the objects are 1 times the mass of the sun. And we go upwards, though, to objects at hundreds of times the mass of the sun. And so that's the range that we initially explore.
Thank you, Patrick. So for the interest of will not be taking any questions right now, but we could, of course, ask more questions during the coffee break. So let me... need to give you a moment. So our next speaker is Professor Tarun Sauradeep from the AYUCA, as well as the spokesperson science of the LIGO India. Tarun is a cosmologist who was originally trained as an engineer, so he's a living example of the synergy between science and engineering. So he led an important and probably the only Indian group at the Planck satellite, which made some exquisite measurements of the cosmic microwave background radiation. And the last several years, Tarun has been playing a key role in shaping up the LIGO India project. And today we will hear from Tarun about the latest from the LIGO India.
Thanks, Ajit. It's a pleasure to be telling you about where we stand with the LIGO India project. Patrick has given an excellent introduction to the field, so I will basically limit my talk to telling you where we are with the LIGO India project. So I call it always an adventure. This is basically what I called it even in the earliest talks that I gave on the LIGO India thing. To me, it is an adventure because I think at least what I felt from my own area, that we do participate in big projects, but we did not have them at home. And that makes a huge difference. And that was why I thought, although against a lot of advice, we felt that it would be adventurous to do this. This is where we stand. What you see here is a rendering of actual building designs which are ready of the LIGO India site. And recently we had a sort of joint discussion with the LIGO lab teams, and many of them felt that this was really beautiful. We do have a lot of improvements over what the earlier labs did in the 90s. Okay, so I just one slide on the promise of gravitational wave astronomy, and since Ajit told you that I come from cosmology, I mean, what really brought me to this field are a few very obvious known things. I mean, it is very clear that gravitational waves are everywhere in the world, because the efficiency with which you can generate gravitational waves is, 10% of the mass of a black hole per can become gravitational waves. Whereas, in electromagnetic thing, nuclear fusion only 0.05% of matter. So, the most energetic processes in the universe are actually happening in gravitational waves. So the universe is buzzing with gravitational wave signals. They are weak, so it's difficult to detect, but weak, and which again goes back to the cosmic microwave background, for example, weak signal, but really uncontaminated, right? And that really tells you the heart of the mechanisms that's generating the astrophysics of the objects. And I think that's very important, that it's unscreened and uncontaminated. So to me, these were really great. And of course, as a cosmologist, you know that 96% of the universe does not emit electromagnetic waves. So mankind should be looking at other ways of detecting things happening in the universe. And I used to put this up just as a catch thing, but I was quite amused. And 2 days back, there was an Aspen meeting where cosmologists got together and have a white paper now on what would gravitational wave astronomy do for dark matter in the universe, understanding the dark matter in the universe. Okay, so the LIGO India project is proposed, was proposed as a joint collaboration between US and India with NSF and DAE-DST. And these institutes, Caltech and MIT, which run the LIGO laboratory, and these 4 institutions, which are the lead institutions of India. Later, I'll tell you that there are a lot more, many institutes involved. The basic thing we have to do is to construct and operate an advanced LIGO detector. And as Patrick mentioned, now the call is for an advanced plus. We have to set up a huge infrastructure of UHV with controls, installation of all the detector things, and build up the team that would operate this observatory, and also the manpower that will actually do the science and engineering with it. The proposed US commitment was that the key hardware components, which are really unique, I can get back to them if you have questions, I won't mention them here, but these are actually really items that have been developed by multiple countries in each of the cases. They are unique in the lasers, the suspensions, the mirrors are all unique. And those are the components that will be coming to us from the LIGO US laboratories as part of this, and we'll work in close technological collaborations on this. The science case was based on this fact that we will be able to do astronomy with gravitational waves. And why is that? So here is a plot, which is again credit to Varun Bhalerao. In fact, this was the plot which we showed when we made a case for this way back in 2016 to the top bosses of the country. And this is light thing that you see is the error ellipse of uncertainty of the first event on the sky. Had there been a LIGO India operational at the same sensitivity, the error ellipse would have been this small. And that actually was the reason one wanted to say that let's go ahead and start doing astronomy with gravitational waves, because we would be able to tell astronomers where in the sky a gravitational wave event happened. So the basic science goal of LIGO India, or science case, has been to allow a full exploitation of gravitational wave observations as an integral part of multi-messenger astronomy. It's already become a reality with the neutron-star merger, but it will become a routine with the entire network of gravitational waves and detectors in a decade from now. And this involves high-end frontier technology, which was understood to be transformational for Indian high-tech capabilities in photonics, lasers, control systems. And that is one of the reasons India was very interested in this. And why would the world be interested in an Indian detector? One thing is, of course, the geographical baseline that this detector provides, and hence the angular resolution of the sources, source localization. But there is another thing which I always emphasize, is India had a demographic advantage. India was not the only country where you could locate the third detector. But in my assessment, if you really wanted to see a country where in 10 years' time you could have 10 times the growth in the numbers, we really have it if we play it right. Okay. And which involves creating research opportunities for UG undergraduates and postgraduate students of science and technology, so that within a decade we will have this. It's also not just an astronomy project, because LIGO India actually reaches out to the astronomy world. So we have synergy with X-ray, radio astronomy, and all this has been borne out with the neutron star case already. We will also do fundamental science, and I think Rajesh will mention some of that in his, in the next panel discussion. This is, of course, allowing us precision measurement, fundamental test. But the main thing which excites me is this. I mean, it touches so many areas of technology where we will be actually forced to work absolutely at the cutting edge. The people who build the detector, people who set up install the things, everyone has to be aware of how things work at the cutting edge of each of these technology. Besides, of course, is computing in Bengaluru. One must say that this is stretching we already in IUCA, for example, have one of the largest computers to do the gravity wave analysis. So this is what the gravitational wave detector looks like. So what Patrick showed you was the Michelson interferometer part, it's actually a Fabry-Perot where 1 megawatt of power is trapped within this between this end mirror and the and another mirror here. And our job is to encase this entire 4-kilometer length apparatus in ultra high vacuum. So this is one of the largest vacuum systems that you would have in Asia. It's one of the 3 ones with 10 megaliters at nanotorr. And this is how the innards of the vacuum system looks. So there are, this one of the themes of this Vigyan Samagam is the industry thing. So I would ask our industry people to note the kind of scale of construction requirements that will come up with LIGO India very soon. We are formally in the construction phase now. And these are these huge chambers that Patrick showed you. And these are some of the pictures of from Hanford, the tube. And in these tubes would be very intricate optical schematic. And this is already a simplified version of the schematics. And so there's a huge amount of precision kind of instrumentation that needs to be set up within this vacuum tube before we can get to work at this. So what's the status? So we of course got an in-principle approval, as Patrick mentioned, very soon after the discovery was announced. And then very soon after that, we had the MOU signed in March, and then we have had continued top-level recognition from the government about this project. And what was very interesting is in the time that we were waiting for the approval, since 2011, we had actually done a lot of homework. So, for example, we had already scoured the country with 40 sites leads and identified a site. And very soon after we got our in-principle approval, we could actually declare which is the site we wanted to build at. And for doing that, we had to carry very interesting seismic studies, very short 2-week to 4-week seismic studies, and with teams going around these various sites, about a dozen sites where we carried them out. And by and large, we found the Deccan area, the Deccan Plateau, is actually a seismically extremely good site. So this trace is the seismic noise at Hanford, and this is the trace of the seismic noise at our site currently we're looking at. So these are promising sites. The site also, to people who are really pushing the project, starts looking beautiful. So this is the dry season, this is post-monsoon, and this is the spring bloom. And you start really feeling that it's great. So this is where we'll have the detector. Already a lot of work of marking out the site, some exploratory excavations, geotechnical studies have been going on, a lot of activity. We have a functioning guest house and LIGO India office close to the site. And I was hoping to tell you land acquisition is 100% done, because any time now or today or tomorrow, we expect that the last 1% of the site, which is going through some procedural step before it's handed over to us, is on, but 99% of the land is actually under our control. And it's not a small amount, it's 174 hectares of land that we had to acquire in this thing. We are formally in the construction phase. Tenders for construction of site office had been issued a few months back, and they are under consideration. We have got the environmental clearance from the state, which involves the Pollution Control Board. And for people in certain projects, they'll realize that this has been something that we were really chewing our nails on. We have finished the geotechnical survey. We have a seismological survey with 5 stations over 1 year that is underway, which has been undertaken by the National Geophysical Research Institute. We have essentially figured out how to get the power and water supply. So we just have to pay for them now. The Niban notes are there. And we also are in advanced stage of campus land acquisition for campuses near the site. sorry. Yeah. So civil infrastructure, as I said, we have detailed architectural drawings which are ready already. Been reviewed multiple times. We also had a few day-long, very detailed discussion of the HVAC and all these issues of how you put the services there. Site leveling plan is being reviewed. We have fairly good advanced equipment layout and mechanical layout drawings. And again, just to show you a picture of this. So this is the central station, which is 20-meter high building here. This is the staging building from where we will be taking stuff and putting it there. This is the operations and offices and operations building out here. I mean, this is not the operations of this detector, but just the offices of the observatory. And then this is kind of a overall campus services out here. For the vacuum infrastructure, again, conceptual vacuum drawings have been ready for some time. The system requirement documents have already reviewed. And we are now trying to put together the execution plan for how we will, get the vacuum, major vacuum fabrication and done. And before that, at this point, we are already, very close to giving out orders for prototype chambers and short prototype beam tubes for testing. We are doing outgassing measurements on the kind of steel coupons that we are getting from various vendors. And on the other side, we are also getting ready to be able to set up a sensitive interferometer. So at RRCAT, for example, there's Fabry-Perot cavity being set up with has control systems. This is happening also at IISER Pune. We will, I think, this LIGO involves 40-kilogram mirrors hanging on glass fibers, and these fibers need to be drawn at site, and essentially that is kind of something that RRCAT is doing now. So these are the project milestones. I just, I don't think you need to go. We are more or less doing fine as far as the phase 1 goes, and we hope to start construction, as I said, very soon, early next year. And the completion of the project would be with after the first joint science run in 2026. So we hope to close down the close down and move into operations and maintenance phase in middle of 2026. So in terms of building up a team in India, here are pictures of series of meetings we have had in Ayuka, bringing in international experts in the field with researchers in allied fields in India from many institutes. And this team is building up. We have working groups within them who have really taken up projects to do that. There's a training laboratory which is there at IISER under a joint partnership with Ayuka. And there are interesting areas in which we are pushing. So for example, squeeze light technology, because we need to be up in advanced plus configuration, which uses quantum playing with the quantum nature of light, which is squeeze light. And then there's this challenge of improved mirror coating, where some groups are working. Then there are some groups working on fiber-based lasers, which are equally that stable and narrow line width. And then there are other challenges of mitigation of noises that are really exciting areas. And even we have engineers working on actually the wind loading noise, which has been a problem with Hanford, and we are trying to make sure that our site does not suffer from that. We have a very large data center with already, which is part of the LIGO computing resources as a tier 2 data center. And there is a data center at ICTS, which also is gearing up here. Another thing that has happened is while initial years LIGO India stood out as a not very clearly as Astro project, I think astronomers have taken to it after the binary neutron star merger. There were 10 Indian faculty from 9 different institutes involved in papers, follow-up papers of this event, and GMRT has been taking data on that. AstroSat had something to say about it, and ISRO is actually considering a dedicated mission for having a constant monitor called Raksha, a pair of satellites which will go around the Earth and make sure that we don't miss out a signal corresponding to a gravitational wave trigger anymore. The LIGO India Scientific Collaboration, which is one single group in the LIGO Science Collaboration that Patrick mentioned, has been growing steadily. So you can see these are the numbers of people involved. The FT, the full-time equivalent, is growing fast. And also the fact that the number of authors is leveling off means we have actually more people joining in the collaboration as members who are doing technical work of actually building the detector. And we already have 15 groups. And this is the kind of really the idea with which one wanted to start off with LIGO India when, Bala and few of us wanted to talk about it. Before that, in the initial LIGO stage, India had one group in the LSC from 2000 to 2010, and that is now a 15 institute, 93 member group. And I think this is quite amazing that we are participating in such a large number into this. So to sort of summarize, we have continued top level support, and some key people are here, and we have the site acquisition well under control. 99% is done, and plans for civil and vacuum under control, and we have off-site facility coming up. We have a very developing technology development and capacity building plan, which is going fairly well. And these are challenges, of course, and every aspect of it is a challenge. I don't mean to say we are doing, when I'm saying we're doing fine, so far so good, but I think the challenges ahead are enormous. So I'll want to stop with this picture that Patrick already showed, only correction being that I've sort of taken the liberty of saying LIGO India is also under construction now. And thank you, and please join us.
Thank you very much, Tarun, for this nicely summarizing the current status of LIGO India. Maybe Tarun can take one quick question.
Okay. Yeah, it is at Ondha. Ondha is a town in the Hingoli district of Maharashtra. And for people in Maharashtra, this is also well known because there's a very well-known pilgrimage site called Ondha Nagnath, which is about 10 kilometers from our site.
Thank you.
Okay, thank you.
We start the panel discussion. We have 3 panelists. One is Professor Bala Iyer of ICTS and the chairperson of the Indigo Consortium, which sort of spearheaded the initial efforts for building the LIGO India, and a theoretical physicist who have made pioneering contributions to the theoretical modeling of gravitational waves. And the second is Professor Rajesh Gopakumar, director of the International Center for Theoretical Sciences of TIFR, and who is a theoretical physicist who have made important contributions in gravity as well as in quantum field theory, especially string theory. And Dilip Krishnaswamy, who is a computer scientist from the Reliance Geocom, who, apart from being has done interesting work in computer science, have started making very interesting contributions to the data analysis of gravitational waves from a computer science perspective. So they would be speaking on different aspects of the promise of LIGO India on different fronts. So let me first ask the panelists to be on stage. So what we thought was we will start giving an opportunity to each of the panelists to say a few words about different aspects of the impact of science, of LIGO India in the science and technology and societal aspects of LIGO India. So we will start with Bala here.
Okay, so welcome to this panel discussion on the LIGO India project. So let me begin with some statement on where we are. And as Patrick sort of pointed out, it's a 100-year-old history. So of all the fundamental interactions, gravitation is the weakest, yet being universal, as GR revealed, it determines the extreme end states of stellar evolution and the large-scale structure of the universe. The transition from back waters of physics to the center stage was triggered by the discovery of pulsars, quasars, and the cosmic microwave background in the 60s, and their consolidation later into relativistic astrophysics and the precision cosmology, which I would say led to the first golden age of general relativity. Yet all that electromagnetic astronomy reveals adds up to a tiny 5% of the universe, and the rest, dark matter and dark energy, are still mysterious. The first direct detection of gravitational waves from binary black holes in 2015 heralds the dawn of what I will call as the second golden age of general relativity. For it was not just the first direct detection of gravitational waves by LIGO, but the first discovery of gravitational waves from a binary black hole system, and the first discovery of a black hole more massive than ever observed before. An event which is not accessible to any electromagnetic observation. And it was relieved solely by Einstein's new messenger from an event 1.3 billion years ago, when life was just transiting on the Earth from unicellular to a multicellular form. It took a century to realize because of the technical challenges, and it has been an odyssey of a large collaboration and the synergetic coming together in the present age of technology, experiment, theory, computation, and importantly, big science. The other thing, as Patrick pointed out, was the first detection of gravitational waves from a binary neutron star in 2017 was a spectacular demonstration of the potential of multi-messenger astronomy for the astrophysics, fundamental physics, and cosmology. And it saw the coming together, as Tarun pointed out, of the communities involved in LSC, Astrosat, GMRT, and the Himalayan Telescope. And as has been emphasized, all this was made possible by the existence of a gravity wave network consisting of two LIGOs and Virgo, and the addition of Kagra and LIGO India to this global network will improve sky localization and source characterization over most of the sky, and it will consolidate the success story in the coming decade. So you will agree that it was audacious of the scientists involved in gravitational wave detection to call a facility to detect gravitational waves an observatory. But you will agree that the O in LIGO was remarkably prescient and rapidly earned. And therefore, with the discovery, at the first discovery of gravitational waves from binary black holes, we can say that Chandrasekhar was doubly right that astronomy is indeed the true home of general relativity. Other interesting things also happened, because immediately after the first detections by LIGO and Virgo and the spectacular success of the LISA Pathfinder, it led to the approval of the LISA mission that will look for gravitational waves in the millihertz band. It has also led to a critical assessment of the science case and the technologies for the third generation gravitational wave detectors like the Einstein telescope and the Cosmic Explorer. So it is very clear that a new gravitational wave astronomy spanning over 2 decades of frequency will explore the universe in the coming millennium. Gravitational wave astronomy provides a complementary window that will reveal as yet unexplored aspects of our universe. So it is very interesting that a century since its inception, today, for example, everybody agrees that GR is the epitome of mathematical elegance, conceptual depth, and most importantly, observational success. But still, gravity is an enigma, as Professor Gopakumar will show you. But the strains of the gravity wave symphonies can now provide unique clues to how the cosmic jigsaw puzzle meshes together. So this is really about the promise of gravitational waves. I just wanted to come next to the challenges of LIGO India kind of project. Now, one thing is that the gravitational wave observatory is a challenge, but LIGO India is more of a challenge because in some sense, we are doing initial LIGO, advanced LIGO, and A+ at the same time. We have the advantage that we have the experience of the LIGO US colleagues to put on, and the opportunity is that when it comes online, we would probably be the best advanced detector when it comes online. As Tarun pointed out, since 2009, we have built a community of about 100 people. But when LIGO India comes online, by that time, we probably would need a community of about 250 people around LIGO India, jointly having special skills. So the challenge is going to be, how do we create this group? How do we retain them? How do we grow them to grow the next generation of gravitational wave physicists? Again, so what really definitely is required, and we have been talking about it for quite some time, is a national gravity wave graduate program like the ENO program, or for example, the SIR schools in high energy physics. And I think that the Center for Gravitational Wave Physics that Tarun talked about at IISER Pune probably can take lead in this particular activity, because this is very, very important to happen, because if we really don't have the mechanism to get younger people in, we would be in trouble in the next 10 years. Again, as Tarun pointed out, that gravity wave detection involves many technical aspects, many technologies. And as Beverly Berger of NSF had pointed out, this is an area where every technology they are touching, they are pushing, and there are a lot of different technologies they are touching. When, even though I come from a theoretical background, the reason we really felt that India should have a gravity wave detector was basically because of the fact that it could impact research in these different areas which are allied, which sort of lie at the fundamentals of gravitational wave detection. So the important point is it can impact not only create new information in astronomy and astrophysics, it can impact groups which involve, for example, in control systems, in coatings, in things like lasers. So the fact that these experiments also can benefit from the technologies which come with this observatory is something we should be excited about. Also, naturally, it will bring together experimental groups, engineers, computation departments, and therefore I think we should not lose this particular opportunity, just as the radio astronomy community over the years really has come together from engineering communities and physicists and so on. We are now moving into an age where, since in this we are talking about mega projects like CERN, etc., it is really now interesting that gravity wave facilities are sort of both something like CERN, and they are almost like the Fermi observatories. So we are on one hand something like a fundamental physics facility, and on the other hand we are an observatory, and the working styles of both these communities are very, very different. So how do we become a community which should sort of have the challenges of both these different working styles? This is going to be a challenge which we really have to face over the next 10 years. But it's interesting that this has really been realized by all the working groups who are talking about the third generation, and they intend to work together with CERN, so that because many of the technologies, funding levels, management, the challenges are very, very similar. So I expect, for example, even CERN to start interacting and have probably a small group working on gravitational wave related projects in the coming years. I wanted to sort of end by pointing out that Indigo was the midwife in some sense of the LIGO India project. When we began, we had two twin goals: to have a pan-Indian participation in the LIGO scientific collaboration and to realize a LIGO India observatory. Now, both those things are essentially sort of coming to a close. So what do we do with Indigo? Do we close the Indigo consortium or do something else? But the fact, I think, is that we have had some internal discussions, and we believe that we should convert Indigo into an Indian counterpart of the GWIC. And essentially, it should be an advocacy group for gravity wave research in the country in different bands. because in addition to the Earth-based gravitational wave detection, space-based detection by LISA will become an important activity. Pulsar timing activities are already happening in the country. Maybe one will have a cosmology mission to look for gravitational waves. So probably Indigo can become an advocacy group for gravitational wave research in this particular country. So I think with this, I'll just basically end my presentation. Sorry if I have taken more time than Ajit wanted me to.
No, thank you, Gala, for this kicking up this panel discussion. So before we open up the panel for questions, let me ask Rajesh to make some introductory remarks.
Hello. Good morning, everyone. I'm Rajesh Kumar, and from the International Center of Theoretical Sciences. I'm here sort of wearing two hats, both as a theoretical physicist and also as heading the institution. So Ajit asked me to sort of touch on both aspects. So let me start as a theoretical physicist. So personally, I think, though I'm not involved directly with the gravitational waves and the physics immediately from gravitational waves, my area is more on gravity and properties of the quantum level, which is something that string theory aims to understand better. But it was nevertheless a very exciting moment for me when I heard about the discovery of these gravitational waves. You saw the signal, and some of the aspects of that signal are things you learn theoretically about how this rotating black hole relaxes to its final state. You see these ring down modes, and to actually see them measured was incredibly sort of empowering, or felt that wow, all those scribbles on a piece of paper, you can actually see them here in this measurement. So from the point of view of a physicist, this discovery was a momentous event, and I think it has excited the imagination of a lot of young people in both the theoretical as well as the experimental aspects. I was very happy when I heard Patrick mention this meeting in 1950s at Chapel Hill, where a lot of theorists actually helped to figure out the existence and the possibility of gravitational waves being actually real objects that you could work out. I mean, in some ways, right now we are in a similar stage with respect to the quantum effects that in gravity, and I feel that 60 years from now, perhaps this will be the moment. 2015 will be the moment when you sort of opened out a new chapter, which eventually would lead maybe 50 or 60 years down the line to being able to measure some of the exquisite effects of quantum in gravity, which have been studied by theorists now, but which at the moment look quite out of reach, but perhaps the similar kind of ingenuity that went into these developments will eventually lead us to measuring the properties of the event horizon of the black hole and the kind of Hawking radiation perhaps that is emitted from them. So this is, I think, in fact, amongst many theoretical physicists, there's a saying that black holes will be the hydrogen atom of the 21st century. So just as hydrogen atoms sort of revolutionized understanding the atom, revolutionized our understanding of physics and broadly even technology in the 20th century, black holes, as Chandrasekhar said, are some of the most perfect objects in the universe, and understanding them both at the classical and the quantum level can perhaps open out very new frontiers in the 21st century. And in fact, there are remarkable ideas out there right now about the relation between black holes and quantum information, and how black holes may be perhaps the best ways in which you can encode quantum information, which might even lead to developments in quantum computing, which are, so this is how the ideas in physics sort of circulate and sort of fertilize each other. So that's, as a physicist, something I wanted to just convey, how you open out new horizons. at the institutional level, again, this is a remarkable opportunity for India, for Indian institutions. We heard some of that in Tarun's talk and so on. And Bala also mentioning, I think it's the discovery and a lot of the publicity, especially from the highest levels, that the discovery got has helped enthuse a lot of students. We see this in our outreach events, that young people come and there's a hunger to know what's going on, what are the things you can learn. People want to participate, and I think, as we just heard, there's scope for participation from physicists, from engineers, from computer scientists, whole sections of people, and India has this demographic dividend which we can capitalize on. And I think the Vigyan Samagam that way is a great venture, and I hope the publicity generated by this caravan moving through 4 cities will draw in many more young people to LIGO, but also the other science projects that India is participating in. So I think as institutions we can definitely use this as a way to showcase how you can work in India and produce world quality science in a way which was not possible in a previous generation. I think it's important that we train very good undergraduate students and graduate students and attract faculty back to India to work on these. And I think the presence of high-level cutting-edge projects like LIGO India will help to do that, will help to bring a lot of people, high-quality people, into science in India and participate in whatever capacity they can. So it's a great opportunity, and I think institutionally we should all capitalize on this. I think the idea of these training schools is another. I think we can't capitalize on this demographic dividend unless we properly train people. So I think I heard one of the people who was in charge of the SK in South Africa once give a remarkable talk about how right from the school level they have been sort of trying to draw people in as interns and so on, get them enthused at different levels across from undergraduate to PhD. So in a country like South Africa, they have really used this as an opportunity to get people into science. And I'm sure in India, with its much bigger population and base, we can do a great job on this. So I think all our institutions need to get our acts together, maybe even coordinate with each other on some of these things, so that there's room for a lot of things to be done. So I don't think there's danger of anyone stepping on anyone's toes. We can all do our share of adding to this. Thank you.
Yeah, thank you, Rajesh, for this very thoughtful thoughts. So let me then now ask Dilip, who is an engineer, to give a different perspective from the side of computer science and engineering on this.
Yeah. First, I want to say it's great that this event is at VITM. I came here as a schoolboy looking at pulleys and prisms and lenses and magnetism and electromagnetism in action. So it was beautiful to be here, and glad it's happening here. I'm an engineer with experience, still with a schoolboy a passion for physics, and when just my story, when the discovery event happened, I just felt like, hey, how do we find out where the event happened and things like that, and so I got interested. But as I was trying to understand how this work is happening, it was amazing to see that it's not only physics at the extreme, but it's engineering at the extreme. And if you're experienced in electrical engineering or mechanical engineering, there is a treasure trove of research engineering opportunities here. And it's not only world-class scientific research, it's world-class engineering research that you can accomplish. especially with the increasing sensitivities that have to be designed into the system. It'll be amazing from feedback control systems and sensor engineering and all of that. And with regard to communication systems, if you have a background in terms of detection theory, noise cancellation processing, or inverse source signal analysis and things like that, you will have a lot of fun in this space. And as a computer scientist, a lot of people are doing analytics for mundane tasks these days, but we could leverage AI and machine learning, deep learning kind of technology as well, and hardware implementations as well. So to actually do the processing faster potentially. So it's an amazing opportunity, and I think even in the curriculum we do have engineering physics programs, and maybe that could be tailored to bring in some of these engineering subjects that would be needed to train the engineers for LIGO India, including like advanced control systems theory or sensor systems communications. If you make sure that those aspects are covered, I think the products of those engineering physics programs might be ready to actually get out to this, and it should be a really fun ride. Thank you.
Thank you, Dilip. So let me thank all the panelists first, but now we are also open to questions and comments from the audience.
Yeah, this is response to Dilip's nice comments that you made, especially preparing, let us say, the engineering students in general these days coming back into the science fold, not necessarily only actually doing the top class science, but also contributing significantly in terms of top class technology that you talked about. It's true that there has been a kind of a lag between preparing them on the technology front, but I must share with you these days even the engineering colleges are actually pumping more of AI, machine learning, deep learning, etc. into their syllabus. As far as engineering, physics, and such kind of basic science things are concerned, they are taking a beating just because there's too much they want to pack in those 4 years. But I must also tell you that at least there are 2 colleges that I see now. They went ahead and actually made a 4-year undergraduate program in artificial intelligence, which is something quite remarkable, and also I think quite difficult to think maybe let us say a year or 2 back. And also another point that I want to specifically ask you. So taking these tools, ML or DA, etc., into basic sciences, there has been some work maybe using different names. Maybe people were not calling them as machine learning, etc. But how do you actually, is it because it's getting a little easier to train them on the engineering problems, but training them to apply the same techniques in science is not something is equipped in the colleges, especially because the faculties were not trained in those aspects. So do you have some thoughts about, it's not just only training students, but actually training faculties to ensure that the same techniques could also be leveraged on science?
Yeah, people learn a lot of different techniques in AI, ML related courses, but to really be relevant, you do need the domain knowledge. So you at least try to get in as deep as possible and collaborate with a researcher who's experienced. I believe in the LIGO India program, they want to bring the engineer, pair up an engineer with a scientist kind of thing. And that kind of collaborative activity will actually help. In terms of academic programs, I think we can, with the advisory board that we might have for LIGO India, they could probably help in tailoring the curriculum and things like that. There are different techniques that are out there. We are looking at significant amount of data is coming every second, at these detectors. And as they said, they have millions of templates to continuously correlate and identify, where the signal came from and what was its characteristics and so on. So it's a tremendous amount of data processing happening in those huge data centers that are there, and valuable research that's happening. So it can be a lot of fun, but it would need some domain knowledge as well being imparted into the curriculum as well, and then you can go a little deeper. Maybe a specialized course could be offered that goes a little deeper into the math, and then people can start thinking about how they can apply their knowledge into the domain, right? Yeah.
I'm sure some of these challenges are shared by other mega projects also, and possibly there are successful examples of this, which maybe someone like Srikumar or Ishwar could comment on. But before that, let me come back to Arnab.
Okay, as several persons pointed out that this LIGO India will have tremendous engineering challenges, and we heard that from vacuum technology to laser, there are many other engineering challenges. So my question is, which particular aspects of technology aspects are going to be most challenging given the present expertise in India? And those challenging aspects, if further research has to be done, is it more appropriate that the research will be done in some of the private companies, or will it be more appropriate research to be done in some of the academic engineering departments like in IITs or IISc? So either Dr. Dilip or anybody else may respond.
Paula, would you like to take that question?
Yeah. I will begin the answer, and then probably Tarun can take it over. So as you rightly pointed out, there are two sets of problems. One thing is, with the current LIGO India, there are challenges which come from our knowledge of what happened in the LIGO US sites. So as he said, these problems are identified, and we are basically trying to get groups from places like IITs and some engineering colleges to really tell them what the problems are. And we have found that they are interested in participating in trying to find solutions to these particular problems. So for example, the wind problem was one which was mentioned. Also, for example, in terms of the seismic improving the low frequency behavior of the sensitivity of these instruments. So these activities essentially are you, as you said, finding the right kind of people in the IITs. They are basically doing this kind of work. The other set of things which we are really facing is, as I said, since we plan to go to the A+, the kind of technologies which are involved are sort of things which require fundamental research which is happening also outside. For example, the optics is supposed to be made from silicon. The laser is supposed to be 2 micron rather than what is being used now. So we find that there is some interest in this kind of activities also in some groups which are outside currently the gravity wave groups, for example in ICERs and in IITs, etc. And they are being given specific projects by the LIGO India R&D wing, and that Tarun can probably say something about. It was his last slide in his talk, so maybe he can emphasize on it.
Thanks, Nub, for bringing it up. So I would say that work in progress. I mean, this is a big challenge in front of us. So LIGO India has a scientific management board, and I happen to be the member secretary of that, and one of our job is to create this manpower base and with the current training. And we have been really scratching our heads as to how would be the ideal way to have a viable training as well as an R&D program. So R&D program is also meant to generate people who would train. And one of the things which Rajesh mentioned, which we have often shared, is this thing which one should realize is, I mean, there are enough for many, many institutes to work in this area together. And whether we can come up with a model where training is distributed in many areas with a central coordination rather than just a training school where people come in and learn a set of courses taught by this thing. One model that I have been thinking about is whether we could sign up institutions to be taking up students for certain so you'll have modules of things, lectures, and some hands-on work that they go and learn at various places. And that would require a cooperation between institutes on a much bigger scale than I have seen before. And I think, one of the reasons, someone like Praveer or someone can comment on from his many years at Mega Sciences in India, whether such a model is something that we could think of, where, we sign up like, we have the Center for Gravitational Physics and Astronomy with IISER Pune, but whether we can have a entire network of such things where a central coordination is done to make sure the right students are matched to right places for, getting exposure to the areas, and then probably work at one of the main centers.
You asked me a very tough question. And,
yeah, it's a tough
and I have no answers. But I am actually, I've been thinking, because one of the, even there's a more fundamental question. If you look at these areas, I think astronomy is not even taught in most of the institutions, higher educational institutions. We have a very fundamental question. So I think in manpower training, as I have mentioned in many of these PMB meetings, I think we'll have to go through a short-term plan, a medium-term plan, and a long-term plan. And you'll have to attack these things. I really have no answer, but I think there is, I think collaboration and cooperation is the name of this game. Otherwise, we are out of mega science. Because if you look at India, any community in physics and any of these areas is about researchers of 150, 200, 300 strong. It's not a very large community in any of the areas, except maybe condensed matter physics and material science, which may be a little larger, 500. So I think we have a great challenge before us. So I think we'll have to really work on this problem. I have no solutions at the moment.
Okay, so unfortunately we have to wind up in 0 minutes. But before we conclude, let me ask a very quick question. I was told that we have 0 minutes. So before we wind up, let me ask one last question to Rajesh. There is one problem of how to make this project successful. The second is how a project like this can be used as a vehicle for, in some sense, taking our theoretical research to the next level. Do you have any final thoughts on that?
Hello. No, I will just like to say that it really opens up many theoretical frontiers. Yes, it really opens up a lot of theoretical frontiers, and I think I see a lot of young people excited by that prospect that they will be able to perhaps address a whole new set of questions related to the quantum aspects of black holes. I think it is really quite remarkable because black holes theoretically have properties which we are just beginning to uncover. They are, in some sense, they pack a lot of information into the smallest possible volume. They are very efficient scramblers of information, as they say. They thermalize very fast. So they are, in some ways, some of the most ideal objects possible, and that's why, in a way, Chandrasekhar was very prescient when he mentioned them as some of the most. So learning about their properties is going to tell us a lot about real systems also, which we are using to store information, about their thermalization properties, their so on. So I think there are a number of frontiers theoretically that are open, which by having a possibility of testing them with future experiments, I think we are just going to begin understanding even a lot of the detailed classical properties with some of the tests in the next couple of decades. But going ahead, perhaps we can test more of the ideas beyond Einstein, what is really there. And I think that's something very exciting. Also with the Event Horizon Telescope, which is measuring a different set of black holes, the supermassive category, which again, I think some of the other radio telescope ventures in India and around the world will hopefully help to image black holes better in the radio wavelength. So that's another place where we can learn more about black holes. So so I think it's a very exciting time for us to be a physicist who is interested in these aspects.
Interesting seeds of thought, and some abstract, some more concrete, and I hope that some of these more concrete ones, like the institutional collaborations, etc., we could take ahead, and with the help of multiple institutions and agencies. So let me thank all the panelists and the speakers of the session, and all of you for attending the session. Thank you very much.
Okay, so we should have been into INO session in 5 minutes, but now things are not even tea is out. So can I request all of you to come back in let us say 15 minutes, which will be 11:50. Okay, 15 minutes. In 15 minutes, let us have a quick cup of chai and come back because things are getting quite delayed. Okay, thank you.